So, good afternoon. It's a pleasure for me to introduce you to Ryszard Nest, who talk about towards resolution of Poisson singularities.
Thank you very much for having me here. Now, there's only my name on this slide, but all of it is, well, most of it is joint work with Eva Miranda. And whatever nice pictures you see are hers. Whatever things you cannot understand would be mine. That's why it's only my name on that one. So you can more or less see something about the plan of the talk. I changed things on the way slightly, but to begin with, things you certainly know. So, but I just wanted to say something about that. Yeah. So, sources of Poisson structures. So, reason that I want to talk, everybody here knows everything about Poisson structures more than I do. But the reason that I wanted them is that because there are certain special kinds of Poisson structures that one runs into in praxis, right? In I don't know, in mechanics, in analysis. And since I'm more of an analysis person in the background, I really want to say, to put emphasis on certain points there. So, so there are these examples. So the first example is, well, free-body problem, and it's kind of simplified free-body problem. So planar, one of the bodies has mass 0. So I won't read through all of it. It's just something you can read in any book in physics, right? You start with a free-body problem, one the body has 0 mass, the other two move independently, and you end up with this kind of, you have this Hamiltonian system. Because of this trivialization of the mass, you end up with actually with a singular symplectic structure. So, and the singularity is something like 1 over x to the cube, where x is the, well, is the variable in R plus. We see these things again a bit later. So it happens to be integrable, so that's a kind of problem you can solve. Let's take another one. Well, that's one that Eva told me about. I didn't see it before, but when I looked at it, I started thinking that I'd been playing with such things at one moment. So it's question of quantizing gravity and such. Not that I know how to do it. Okay, so so example is the pseudo-Riemannian manifold. You look at the space of geodesics. Well, if it's a reasonably nice complete manifold, then space of geodesics is the same, basically the same as the tangent bundle, and that splits into the part which is well, space-like. So there are two space-like pieces. There is a time-like cone, and there is time-like part. There's light-like cone, and there is time-like part. And the two parts, plus and minus, are, well, even-dimensional, symplectic. And then there's this cone in the middle, which in general is not really, it's kind of co-symplectic. It's not really Poisson. It's not really contact manifold. But in 2 dimensions, it is a contact manifold. And so this space of geodesics becomes Poisson structure. Another example, actually very similar to this one, is, well, let's take 2 manifolds, x and y, and suppose that you have a full integral operator from x to y. So such a full integral operator produces, well, has a total symbol. Won't talk much about it at the moment, but then you use this total symbol to do the following. You take the cotangent bundle of x. You could think of it as a cosphere bundle of x. In principle, one usually talks about cosphere bundle of x, but cotangent bundle of x is actually better. So you take cotangent bundle of x, cotangent bundle of y, and this symbol of operator actually allows you to glue those 2 cotangent bundles at infinity. So you get a Poisson structure. Well, it's singular because at the boundary there is a singularity. It's not quite a manifold. It's not Hausdorff manifold. There's a question of orientation. But analysis works perfectly well on this one. And actually this shows up. So this concrete example very much shows up in life. So given this fully integral operator, since it's elliptic threadform, it has an index, and the index of this operator is really a characteristic class of this Poisson structure. Yes? Okay, is it better? Good, thank you. So, you have this Poisson manifold, and its characteristic class is the index, it's an integer actually. So it's something that Alan Weinstein pointed out, that or proved actually, that this actually tells you something about the relation between Laplace operators on x and y. So it shows up very much in the real life. So next example. So, well, I did put quite a few names there, or quite a few terms, because it's something that shows up in different situations, in different contexts, with different names. So here apparently is something called the Radko surface. Okay, so it's Poisson structure, let's say typical Poisson structure of the two-sphere, which has the singularity cell in the middle. It also shows up. So actually, this kind of thing really shows up as it's called Beilinson log divisors. So Beilinson first started studying these things when there was something with analytic algebraic geometry. It's quite some time ago. Then, well, there are these quantum homogeneous spheres, which actually related to this picture, and I will come back to it at one moment. And they are called Podlish spheres, actually. And in this case, the Poisson structure has singularity. So it has linear singularity. The corresponding symplectic form blows up at the equator. So it's like 1 over x, where x is the distance from equator. So there's this, lately there was quite a lot of activity on the subject. Actually, there are at least 2 talks in this conference about the subject. So these are called, this kind of structures, they are called bisymplectic. Well, I call it bisymplectic because it came to us as bisymplectic, but it's called also Poisson structures. So you can translate between this Poisson and symplectic freely in this case. A bit more about it later. So example, you just take circle cross n, where n is regular, and when you pick up a Poisson structure of this form. So pi is a Poisson structure on n. So then you take f theta d by d theta. Theta is the variable in the circle, and each time you have a zero of this function f, you get the singularity. So in this case, you get just a bunch of these, think of it as a bunch of these different equators where Poisson structure vanishes linearly. So that's another example. Well, the one which for me started with B, whatever structure, was Axel Melrose, who wrote a book on this kind of stuff. Not really. So he wrote this book about index theory for manifolds with boundary. So what's happening here is, well, you look at manifold with boundary, you pick up this normal coordinate x, so normal coordinate close to the color of the boundary, and then you can construct a, well, kind of Poisson structure, or a standard Poisson structure of cotangent bundle, and the standard symplectic structure of cotangent bundle, but at the boundary, it blows up linearly. So it looks like this close to the boundary. So 1 over x d by dx by times d by dy, where x and y, x1, y1 are the dual variables. Well, let's say something. So, well, another example, still Okay, maybe I should say like this. So you think about this bisymplectic manifolds. So what Melrose did was to look at the manifold with boundary, choose this kind of symplectic structure or corresponding Poisson structure, and construct the calculus. Oh, well, maybe I should be careful with the word calculus, and construct operators with this kind of symbols. Okay, so this Poisson part of the commutator of the two symbols of operators is actually, well, x1, dx1, dy1, has the singularity. So something would, first of all, there are two statements. So one statement is actually a theorem, but when you think about these products, symbol products on this kind of bisymplectic manifold, so there are obvious different possibilities of constructing symbol product and star product of formal deformation are actually more or less the same. Okay, in the case when you have a homogeneous manifold, then star product and symbol product are the same. Just question of language. So the symbol product here, well, or in general, is classified by corresponding cohomology group. So whatever this HB is at the moment, I'll tell you about it later, and you also hear about it in the next talk about these things. But there's one thing that happens here. So first of all, the symbol, if you think about the symbol calculus, in the interior just have cotangent bundle with standard symplectic structure. Deformation of symbols, a standard deformation of cotangent bundle. So given by symbols of full symbols of sequential operators. On the boundary, something happens. First of all, the boundary itself of this cotangent bundle becomes has a dimensional and symplectic foliation. So there is a corresponding formal algebra is the deformation of this codimension one symplectic foliation. So it's kind of well, basically foliation algebra, foliation star algebra. So in the direction of these symplectic fibers, you do the convolution, so like products of different operators, and the transversal direction. Transversal will be the direction of y1. Remember, x1 vanishes, but y1 is still there. And in this case, just a fine, so it's commutable variable. So you have this algebra. So first of all, so the boundary, you get this kind of foliation algebra that's Melrose called indicial families. That comes naturally because you have this boundary. On top of it, so you usually know that there are traces on the operators. Yes?
We'll just switch the microphone because that one has some resonance. So
okay.
Switch this one off. Yeah.
Okay, I'll try to use that. So, can you hear now? Yeah, okay. So you know that all these algebras, usually there are traces, right? On these deformations of functions on symplectic manifold or corresponding algebras of compact operators or traceless operators, there are traces. Well, in the case of a boundary here, when you have this boundary, there is no trace. So this algebra has no trace, but that's kind of a result of this boundary effect. Well, in analysis, when you have algebra with linear functional, there is a replacement for trace property, which is called Kms property, and that actually has something to do with certain one-parameter group of automorphisms. So one-parameter group of automorphisms has a generator, which in this case is a vector field, and that's what you know is modular vector field. Okay, that's actually the source for Alan's definition of modular vector field. The idea came precisely from this. Okay. Okay. And it is a side excursion, but still it's worth saying something about. So I'm really talking about things with boundary, right? Really, these B structures or all these kind of singular structures always come from some kind of boundary. And so what's happening here is like this. So suppose you have a manifold, compact manifold without boundary. Well, you have differential operators, they get products. You can take functions of differential operators, and you get an algebra. You can invert these functions. You get what you call sequential operators. Very nice algebra, very nice calculus. If you have a boundary, you're in trouble because differential operator does not, or say vector field, does not generate a one parameter group of automorphisms. So you cannot translate across the boundary. This really means that your vector field does not define the self-adjoint or skew self-adjoint operator. This means that you cannot take its functions. Okay, so you have to do something. To construct an algebra, you have to do something else. So you do differently. So what Melrose really did, is not that he formulated it like this, he took this boundary and pushed it away to infinity. Okay, so you replace x by log x. So it's not compact anymore, but you just look at things going to infinity and just assume that your symbols are asymptotically independent of this variable going to infinity. Sorry. It's not supposed to. Sorry. Actually, I think I'm supposed to go to a conference in a couple of weeks' time, and there is always these phone calls from England. There is somebody there who looks where people go to conferences and then goes and suggests that they find you a place to stay. I think it's one of those. Okay, I hope it's better. Okay, so that's this one completion, this kind of, you take variable x and you push it to infinity. I said it's not calculus, because for this to be a calculus, to deserve a name, you should be able to take holomorphic functional calculus of operators in your calculus. And you should be able to write down Cauchy formula, Cauchy integral, and get an operator. Problem Melrose calculus is that you cannot. It doesn't work. So instead, you can do this C calculus. So instead, the boundary singularity, instead of pushing boundary away to infinity, you put some kind of conic singularity, something like 1 over x squared instead of 1 over x. And this is actually an appropriate one for things like the Apatow-Singer theorem. It's not what Melrose did, right? Then there is what's called local boundary conditions that you heard of, which happen to be, well, they are local, meaning depends only on difference. You write on some differential operators, which values of them, differential operators which determine the boundary conditions. On the other hand, they become non-local when you really check what's happening. Because you still have this problem that your vector field does not generate one parameter group of automorphisms. It only generates one parameter semi-group of automorphisms. So what you do here is, okay, so you take the adjoints, you construct the algebra, and what you end up with is, again, the algebra in the interior of the manifold is always the same. But this time on the boundary, you get something non-commutative. So this local boundary value problems lead to a non-local or non-commutative algebra sitting on the boundary. So actually the algebra that sits on the boundary is the Teplis algebra. And this calculus is called the Boutet-de-Monvel calculus. Well, there's also this edge calculus, so you can, these are things with a boundary. Then you can also think about corners and higher dimensional corners. You get corresponding what they call edge calculus, or different versions. Okay, so let's go back. So these Poisson structures, somehow the singularities of these Poisson structures are really kind of symplectic or constant rank Poisson structures with some singularities. And in my not experience, but in the cases that I run into, that usually kind of algebraic, semi-algebraic, they have kind of nice structure, right? So let's just recall a general statement. So if you've got a smooth manifold, you've got a Poisson structure. Generally, it looks like this. So you can you have this pick up a point. There is a symplectic lead going through this point. In the neighborhood of it, there is this kind of correction where f is some function which vanishes at this point. So these leaves are lower semi-continuous. Right? And to be honest, something that I was very surprised when I saw what people are doing with Poisson structures was that, well, obviously, there is this F, the singularities, or people spend, I don't know, 15, 20 years studying singularities of smooth functions. Nobody ever used it in this Poisson situation. I'm still surprised. That's not what we are doing. Okay, but that's kind of obvious thing to think about. And see what, so if you really want to say things about Poisson structures in general classification and such, that would be the obvious thing to look at. So linear things are done, quadratic things are more or less done. High order, I don't think there's anything done. Okay, so as I said, it's kind of starting, well, application, my typing is sometimes long. Starting to apply this kind of ideas to Poisson structures. Okay, so that's kind of came as E structure or symplectic Lebesgue structure came out from my work with Boris Tsigan about formal deformations, index theorems, but actually this whole story is older and really, I think Bielinson is the first one to use it really, this kind of things. So just as a, well, maybe not a reminder or reminder, if you know about it, it's a reminder, maybe somebody does not know about it. So what's happening is the following. So we have vector bundle, we have smooth manifold M, and we have a vector bundle of this manifold. And this vector bundle has, well, you think about sections of this vector bundle, and these have a, first of all, have a Poisson structure, so there's a bracket. And it's, so sections of a vector bundle of a manifold is really module of smooth functions on a manifold, right? So the only thing we are saying is that this, so these sections is a Poisson algebra over these smooth functions, and there is a Poisson algebra homomorphism to Poisson algebra of functions, smooth functions of the manifold. One should be slightly more careful in the definition, but essentially that's what's happening. So you have this typical example, think of vector fields, think of sheaf of vector fields, and take a subsheaf, and suppose you have some subsheaf which happens to be locally free, so happens to come from a vector bundle. Okay, this would be your example. Okay. So this is your vector bundle of your manifold. It's not a subvector bundle or a tangent bundle, but it's a vector bundle. And examples, lots of them, coming, pick up some nice stratification of your manifold and think of vector fields which are, when restricted to submanifolds, they are tangent to the submanifolds. Okay. So all the applications that you see in the differential equations come from something like this. Another example, silly example, but we're thinking of it. Manifold can be a point. So all we have is we have vector space with a Lie bracket of a complex numbers. Okay, so Lie algebra is an example. Okay. Good. Then, given something like this, since we have a bracket satisfying standard relations, you can define can look at the exterior algebra of a dual of the sections. You can just write down formulas for, well, the RAM differential. If you take the formulas for the RAM differential on differential forms as you know it, involving only commutators of vector fields, just write it down, you get the RAM differential, you get a complex. Okay, that's, I think it's called Cartan-Eilenberg complex. In the case when you only have the algebra, this is really Chevalier-Eilenberg complex of cohomology of the Lie algebra. Okay, but the complex is you just write down things you would write down these were differentials of functions, and things work. Okay, good. Now, symplectic means that our bundle has a symplectic structure. So we have a two form on these differential forms with values in E. And if this two form is closed and is non-degenerate, so as usual, gives an isomorphism between E and star. So that's symplectic, and well, Poisson structure, it really looks like this. Right, so we have this closed submanifold, codimensional submanifold given by Z equals 0. The differential forms in this case, so on top of the standard differential forms, like the ones like, well, differential forms on manifold, you also admit D of log Z. Okay, because we are dual to Z d by dz, so dz over z works. So the differential forms, we have these E differential forms, they all look like this, where omega mu are standard differential forms on M. And well, B-symplectic structures just not just the two form of this type. Typical example. So first of all, the standard facts about the symplectic structures, local symplectic structures hold in this case, actually hold in general for these E-symplectic structures. So for B-symplectic structure, local thing looks like this. So there's this x inverse dx which dy term that we had before, plus transversal is a symplectic structure. It should not be surprising for anybody. Then I have a couple of slides due to Eva. So as I said, there is actually so obvious structures, Poisson structures of symplectic or bisymplectic structures. For me, they do come from some kind of calculi. For example, differential operators or differential operators operates on manifolds. Well, quantization, I would say more about quantization later, but quantization is also part of it. So, well, if we know about quantization of symplectic structures, or say toric symplectic structures, so everybody knows this kind. Knows this kind of knows what Bohr-Sommerfeld leaves are. I will tell you. Maybe you will say later, but you don't. But doesn't matter. Not yet. Okay. And so there is this picture that you have seen, I'm sure. So you have your momentum map, and image of momentum map picks up. There is this polytope, which is in the image of momentum map, and there are these points, kind of integral points in the polytope, which are Bohr-Sommerfeld fields. Similar things happens in this B manifold case. We heard about these things already. That you still have this convexity properties, so you still get this polytope, which is image of momentum map, and there will be those points. I'm not going to talk very much about this one. Plus, unfortunately, it's not very readable. But let's take an example, right? So the simplest example. So remember, there was this Radko sphere or Podlage sphere, or God knows what do you call it. So here it is again. Okay, so we do precisely the same as before. So this B structure, so H is the height. Okay, so the singularity H equals 0 is precisely our equator, and the form is given by 1 over H dH squared d theta. Momentum map is dH. Now these Bohr-Sommerfeld leaves are spheres, so there are these red and blue spheres, the ones on above and below. And now I run into this statement by Eva, which says that, well, there are as many ones, there are the ones in the northern hemisphere, there are the ones on the southern hemisphere, and they kind of subtract each other, so quantization is 0. Well, it's not, right? It's not quantization, but 0. Well, I just quoted this theorem, so that this previous picture is really example of this theorem. So, but I'm not going to read the theorem, but I wanted to say is that now we start to remember. So B calculus, for example, right? So we have this, so Melrose B calculus. So we have this boundary. Now what we can do, we can take two manifolds, one on the boundary, glue them together along common boundary, and we have some standard operators or standard compact operators on one side, standard ones on the other side, and we glue them on the boundary. Or maybe not even because let's take, where is it? This example, okay? Because the same example, basically. So think of it as that's one hemisphere, that's the other hemisphere, and they are glued together, except they are glued together kind of at infinity. So Poisson structure vanishes there. Okay. Now, it is a highly non-trivial quantization, right? So it's really, this really represents operators. What does the operate represent? It represents compact operators on X. So quantizing cotangent band gives compact operators on the manifold. We also have these compact operators on Y, and the whole thing is glued together. So this is actually a bimodule of the compact operators. So it's certainly not zero. Okay, it's still non-trivial quantization, and actually it's an interesting quantization because it gives us some hopefully not trivial geometric information. Let's go back. So what I just said, it's once again, there's also, that was the kind of decalculus of Melrose, right? Where we glued together using this boundary formation. There is some saving hold comes from what's called Bodley sphere. So that's it, right? So what is Bodley sphere? So there are these quantum groups, but now I'm talking about C-star algebraic analytic quantum groups, not formal, not Jimbo ones, so representations of the form enveloping algebra. I'm really talking about quantum groups. So a, say, compact Lie group or local compact groups, what is it? It's really a, did I write something? I think I did, right? So what is it really? You have your group, you look at the algebra of, say, continuous functions on your group, and has a structure of an algebra where product is convolution. And then there is a, so this is a C-star algebra, so algebra which represents all the unitary representations of your group. And then on the other hand, there's this dual structure which comes from product of functions and functions, where you get a commutative algebra of functions, and these two things together form a Hopf algebra. But both one side and the other are topological algebras, actually C-star algebras. So there is a norm satisfying all nice properties, and they are complete in this norm. Okay? And well, you can quantize those. That's quantization as C-star algebras. So you get actually one parameter family of C-star algebras parameterized by Q. So I wrote it this way, okay? So it's the formation of a Poisson structure on SUQ2, but as a C-star algebra. That's very nice. And then the special property of this example, SUQ2. So for different Q, you get actually, there are these two pictures, right? So the group C-star algebra, which is just direct sum of matrices. So if you've got compact group, its representation theory gives you direct sum of matrices. Finite matrices do not deform. It's very rigid. So the group algebra structure does not deform. The other side, function algebra deforms, becomes non-commutative. And in this case, it just becomes, well, it turns out to be constant, independent of Q, as long as Q is different from 1. So as long as it's not trivial deformation, just compact operators with unit added. So it's kind of constant. So now we go to the surface, right? So this was SU2 divided by unit circle. What happens in this case, in this deformation, is that, well, the standard unit circle is still a subgroup of this quantum group. In general, this having a subgroup of quantum group can be pretty tricky, but this circle still is a subgroup. Makes sense to write down a quotient, so you get homogeneous space. Of course, SU2 divided by circle is a two-sphere. Actually, it's one of your Radko sphere, right? It has a Poisson structure with singularity on the equator. And so this becomes kind of quantum mechanical quantization of a Radko sphere. Quantum mechanical, because quantum mechanics produces operators. It's an algebra of operators, right? So you get this one deformation. So quantization, as it happens, all these GQT, so all these spheres are independent of the parameter. Okay, and actually, this so if you look at these algebras, they are much more interesting than just this is quantum SUQ2. So what happens is that we have these two hemispheres, the northern and southern hemisphere. Each one of those, well, this is just symplectic structure. So what you get is compact operators. And these two copies of compact operators get glued over the middle. So I didn't write it down, but you get an algebra basically kind of containing 2 by 2 matrices of compact operators. Quotient is a unit circle. So you get extension of a unit circle. And this has more structures. So this algebra, because of its north and southern pole structure, it becomes Z-mod 2Z graded. So supersymmetric. And it has a corresponding super trace. Now, the statement that Ira made that quantization is 0, it just means that the super trace evaluated at 1 is 0, nothing else. Well, this is for SU2, same thing happens for other compact Lie groups. Okay, what you get instead of this quantum two-sphere, you get quantum flag manifolds. And it's really very, there's a lot of analysis involved there. Okay? And again, the C-star algebra part, so representation theory of a group algebra is not that interesting. What really gets deformed is the functions on the group. That's the interesting part. Also, another thing that happens is worth knowing. So, for example, some homogeneous spaces do not deform. Okay, so in this case, in this nice case, group modulo circle deforms, this deformed sphere. There are some examples actually due to Kasztan-Eddinghoff, which shows that these certain homogeneous spaces of symplectic group do not deform like this. Okay, so back to the thing I was talking about to begin with. So I said, this is the attempt to start analyzing Poisson structures in terms of something much simpler. For me, these symplectic structures are much simpler. I know how to compute cohomology. I know everything about deformations. I can basically construct quantizations of those. So these are very nice for me, right? So let's just think about that. So you can use it. So they have this cohomology. It can classify surfaces. Well, the Moser theorem holds so actually all the standard theorem that you know about symplectic structures hold for these symplectic forms. It requires a bit of work, but it's not very difficult. Also, deformation quantization of these symplectic structures is the same, essentially the same as for symplectic structures. So it's not the one based on concept formality. It's really one based on the Kms construction. And there's good reason why I prefer one to the other. I can prove the concept formality, I can write down the result. Given the Poisson structure, I have not the faintest idea what the corresponding deformation quantization is. Conversely, given deformation quantization, I have no idea which Poisson structure it corresponds to. And there is a good reason, because formality is based on choice of associator. Different associators give different results. Okay, so I know that there's this bijection, but bijection depends on choice of associator. That's not something I can do explicitly. Okay? For theaters of quantization, so for symplectic structures or asymplectic structures, I can do things explicitly. So that's why I prefer this one. So, okay, before I get to that one, a few minutes. So, as I said something about these Bohr-Sommerfeld leaps. So, in this example, so was here, this computation here. Okay, it's really, we are really computing trace of one, and actually, this Bohr-Sommerfeld condition, it's really trace of one. So the formula you saw that Anton wrote actually showed you, it's also trace of idempotent. It's a formula for trace of an idempotent. It's not quite automatic because there are not obvious. So there are explicit formulas for traces and formal deformation quantization. Okay? So if I've got an algebra, say Poisson algebra, some nice structure, I write formal deformation quantization. I can look at idempotents in this algebra, and I can write, I have lots of traces, I can evaluate traces of idempotents. There are lots of formulas, they are in general non-trivial. So for example, it's non-contact tori that we had about today at one moment. So a Bohr-Sommerfeld condition was something about trace being equal to integer. Right, so and this comes from the fact that you pretend that you take your algebra of functions on a compact manifold and you do finite dimensional quantization. So construct finite dimensional Hilbert space and action on this finite dimensional Hilbert space. And given idempotent, you have this idempotent on this finite dimensional Hilbert space, you can take its trace, that's an integer. Okay, so that's this Bohr-Sommerfeld condition. If you take non-contact torus, it's already not true. So as soon as this parameter epsilon, I think it was on the previous talk, is not rational, the corresponding algebra has no finite dimensional representations, number one. Number two, there are two idempotents. There's one and there's another projection, and the corresponding traces are not rationally related. Okay, so if trace of one is one, then trace of the other idempotent is one over this epsilon. Okay, so things start happening almost immediately, and actually that's something one should think about when you do geometric quantization. That geometric quantization is constructing Hilbert space is kind of strange idea. Because there's one Hilbert space, right? For each dimension, there's one Hilbert space of its dimension. Whatever you do, it's the same space you get, right? What is really interesting is this algebra that you get out of functions on your manifold or Poisson structure with Poisson bracket or whatever it is. You get some kind of algebra. Well, you want really analysis, kind of C-star algebra, and in general C-star algebra, not finite matrices. As soon as this Bohr-Sommerfeld condition is not satisfied, so there are traces whose values are not integers, you do not have finite dimensional representations, but you still construct an algebra, kind of C-star algebra, and then you can look for representations of this algebra. Of course, you have to be careful because once you have this, say, non-contact torus, there are lots and lots non-equivalent representations. So gluing together different representations is almost exercise in futility. As really representation, inter-representation of spaces. So I have to be very careful what one does there. Okay? But still, that's what comes in life. Right? So these stupid non-contact tori, they also show up in life. So they just have something to do with the magnetic field through superconducting ring. Okay? So in fact, you see these things but in experiment. So I did see this, I did some experiments, and once I was involved in some experiments in low temperature physics, and yes, I saw these things. Actually, apropos that one, apropos Hilbert spaces. So I was in a group in England in low temperature physics, and we were doing some experiments with one of these superconducting rings. So at one moment I sat down, so we got some results, interesting results. So I sat down and I wrote some kind of Landau-Ginzburg model and some kind of computations of this type. Then I went to the head of a theoretical physics department there, and I said, okay, so I would like to talk about it with you. So he looked at it, and his reaction was, well, as long as you don't show me the wave function, I don't bother to talk to you. So that's when I went from physics to mathematics. That was enough. It's true story, by the way. So anyway, as I said, all these structures appear, but let's just go to what I want to talk about. So, well, it's not really, but it's part of it, right? So that's an idea, that's kind of old idea of mine where I was curious about. So there are these asymplectic structures which produce Poisson structures on manifolds. Take a manifold, write down some this symplectic Lie algebroid over your manifold. You get Poisson structure, and somehow it's much easier to work with because you have a symplectic structure hanging above. Right, so somehow you get more info, you kind of resolve the singularities. You just forget singularities, not forget, but kind of resolve them. Right, so the catchphrase, something that we started to work on and talk about, is really that generically we want to think of Poisson structures as kind of induced by asymplectic structures. Of course, there are obvious restrictions, right? So restriction number one has to be kind of semi-algebraic singularities, right? If I go singularity like e2 minus 1 over x squared, but you can't do anything about it, right? So, but in all these examples that I ever run into, they are semi-algebraic, so that's not a problem. So, what was the idea? So, suppose I've got this Poisson manifold, look at the symplectic foliation. Suppose because now that gives me a nice stratification, right? So, then my Lie algebroid will be the one I talked about before. So, look at vector fields which are tangent to strata. Okay, it's a Lie algebroid. It's if you are careful, you get a symplectic Lie algebroid. And the idea would be that Poisson structure should come from something like this. Well, example you would take is take Lie algebra. So Lie algebra is a simple Lie group. Look at this dual, it has this Poisson structure. So this standard Poisson structure on the dual of the Lie algebra. What can we do with it? So you look at it. Well, it has stratification. So or if we think about orbit space, the symplectic orbit space, so it's really G star modulo action of a group. Well, this is already not nice, right? It's not a nice manifold. It's manifold with, well, singularities. Actually, with one singularity, it's kind of conic singularity in the middle. So it has a singularity. So it's not straightforward. So we have to do something else, right? So, as I said, there's invariant theory coming in because there's this singularity at 0, right? So, picture, right? So the picture, again, all nice pictures that you okay? So the picture. So we take, say, SU3. Okay, that's an example. So it has stratification. So we have this, you think about cutting the thing into Weil chambers. There should be some roots here, but some simple roots, couple of simple roots. Okay, so here and here, one here and one here. You pick up a Weil chamber. Then the generic orbit corresponds to, say, interior, to any point in the interior of Weil chamber, produces a generic symplectic orbit of our structure. And within each of these components, so components meaning open set here or open set here or 0 point. To each of those corresponds the symplectic leaves of the same dimension, which are actually equivalent, actually isomorphic. And what you want to do is, well, okay, so there is this, remember there is G acting on G star. So we have to look at what's the quotient. So what we do is you look at the Weil group. It acts by reflections in the simple roots here. Okay, and orbits of a Weil group in this, what is it, this T star, correspond precisely to orbits, conjoint orbits, so split orbits. So actually what you really have is one of these Weil chambers modulo action of a Weil group. It's non-trivial because the Weil group will flip the walls of a Weil chamber. Okay, so you really got some non-trivial kind of polytope, actually, singularities. Well, that's what I said already. So if you think about restriction map from G star to T star, that's a Bott theorem, actually, that it intertwines action of a group on G star and Weil group on T star. Okay, and now pick up one of these generic points. So point here, for example, the corresponding generic orbit looks like this. And then what you do is to look at this picture. Okay, T cross this generic orbit. There's a map down to G star. Well, there's a straightforward map to G star. It's not bijective because there's a Weil group acting. So, so the image is really T star cross O lambda over W. Okay. On the other hand, this has E-symplectic structure. And this is this is really a finite covering of G star. So what's happening is that you have our G star, and there's a finite covering of that one, finite Poisson covering of that one, where Poisson structure is an E-symplectic structure. So there is this symplectic Lie algebroid sitting over that, which produces Poisson structure. Okay. Well, the nice example, the simplest example, and the one where you can just sit down and write things easiest without thinking. Think of SU2, right? Then it's a rank 1 group. So generic orbits are just circles, CP1. We remember that these generic orbits in this case are flag manifolds. That's the simplest flag manifold you can think of. Okay. This blow up here. So R cross O lambda. So R cross O lambdas, this is really R3. So this is the R, so think differently. This is R3. Okay? And what we are doing is we are thinking about away from zero, which is have our concentric spheres, and we are really blowing up singularity at zero. Okay? So, well, it's blowing up, so we really get a kind of two copies of our R plus, actually. Okay? So that's picture which did I say something? Well, I didn't say something. It's kind of almost theorem, but this is the picture that almost because we didn't finish computations. But this general situation for, let's say, symbolic groups of compact type. Okay, but you have this situation that there is this finite cover over your dual of Lie algebra with the same Poisson structure, and there's a Lie algebroid sitting over it with which produces the symplectic structure. Well, it's already interesting because all linear structures are this type. Okay, at least linear structures do come from the Lie algebras. Now it's kind of another kind of not really claim, but the experience that for Lie algebras, if you can do things, all these kind of deformation, quantizations, anything, if you can do things for semi-simple things, you can do it for everything. We work over real numbers or complex numbers. Okay, it's kind of experience, but something that one should do. Okay, but it's not really that automatic, but this is what typically happens. Okay, so and well, we have a structure. So this is kind of our symplectic leaf, and transversely we get this kind of structure, and if this is linear, we are in the same situation that we can treat with the algebra picture. Well, that is a dream of Eva. So I would let you look at it for a few minutes, Other questions what I'd like to do. So what I would like to do really, it's what I would like to do is this one. Understand geometric quantization of Poisson manifolds, where by geometric quantization, I do not mean constructing a Hilbert space. What I mean is constructing an algebra which kind of represents physical Poisson structure. Okay? Not formal deformation quantization, but I can do really kind of construct the algebra. Once I've got an algebra, I can start constructing these representations and decide which representation is, I don't know, represents the state that the universe is in or something like this. Okay, because it really goes this way. So there's this talk about geometric quantization. It's very good for constructing representations of Lie groups or things of this type. Okay, when you go to physics, there are finite dimensional systems. There's only one algebra in quantum mechanics which shows up compact operators. And then you pick up some representations, but there's one algebra, one Hilbert space. You just take your certain operators and give them different names. Once you go over to something like field theory, that's when we are really in trouble. Okay, because certainly the algebra is not finite dimensional, does not have unique representations, and we have no idea which algebra to construct. And then if you go to gravity, quantum gravity, that's even worse. Okay, because there you have to quantize some non-trivial Poisson structure, and nobody on infinite dimensional space, nobody knows what to do. So 2 weeks ago, I was at a conference about actually devoted to quantum gravity, and the only talk hello, yeah, the only talk which really could say something was not so much a talk about quantum gravity, but was more like advertisement for a certain group of people doing certain numerical computations. Okay, so my dream is to really try to construct analytically quantization of infinite dimensional space. Thank you.
Other questions, comments for Richard?
So another way of desingularizing the Poisson manifold was to looking into the symplectic groupoid, integrating it. So how much is this approach related to the symplectic groupoid?
Well, symplectic groupoid has this tangent bundle, which is symplectically algebraic. Okay, so it's kind of, you are quantizing these are symplectically algebraics, you are kind of quantizing symplectically algebraic. My problem is that, first of all, you can't always quantize symplectically algebraic. And number two, I tried once, not alone, some people, to use these symplectically groupoids to do some quantization or to do something like this. I never really got anywhere. Okay, so really that not seem to, as far as I can see, it does not help with quantization. Plus another thing is it's too big. Okay, so if you take G stars, so you're integrating symplectically groupoids to tangent bundle of G. It's twice too high dimension to do something. But yes, if you have symplectically groupoid, you have your symplectically algebraic.
Other questions?
No, so thanks a lot, Richard, for sharing your
You
dreams.
do have a dreams with us. Okay, and we'll resume in 15 minutes.